Good morning, everyone. So welcome back to our General Physics 2 class. So today it's our honor to have Dr. Tomoki Wada from National Chongqing University as a guest speaker to give a special lecture today. So Dr. Tomoki Wada obtained his PhD degree in physics at Kyoto University in Japan. And after that, he worked as a postdoctoral researcher at the University of Tokyo, Tohoku University, and now it's National Chongqing University. His research focused on theoretical study of high-energy astrophysics. For example, fast radio burst, magnetoburst, and binary merger. So the topic he's going to present today is neutron star, the strongest magnets in the universe. So let's welcome him.
Good morning, I'm Tomoki Wada from National Chongqing University. Today I'd like to talk about neutron stars in universe. Neutron star is, as written here, strongest magnet in the universe. And in this course, I would like to very briefly explain why we know this is the strongest magnet in the universe. Okay, let me start. Oh, wait. Okay, let me start with hierarchical structure of the universe. This is a very brief and very simple diagram of, showing an astronomical object in the universe. This horizontal axis shows size of object, and vertical axis shows the density of the object. And we are here. Typical size of Earth is about 100 centimeter, and typical density of Earth is 1 gram per cc. But there is more small or big object in the universe. For example, when we see more and small object, we will find small object means left part of this figure, and for more small part we find atoms, or at the center of atom we find quark or nucleons. This is small part of this diagram. And when we see more large object, we will find, for example, sun, or galaxy, or universe. And in astrophysics, we treat all of these objects by using principle in physics. Okay, let me start with these objects, starting with Earth. First, we are human. And typical size of human is about 1 meter. I know some of you are 1.5 meter or 1.7 meter or 2 meters. But in astrophysics, we don't get detailed numbers. 1.5 or 0.7 or relatively 2 is nearly 1. Okay? In this class, please focus on this point. Please care of this point. So our about 1 meters. When we zoom out from human, we will find your university, NTHU. Here, I don't know, maybe we are here, I think. And typical size of university is about 1 kilometers. And when we zoom out more and more, we find Taiwan. Typical size of Taiwan island is about 400 kilometers. This is much larger than. Is it okay? This is much larger than humans, but it's still very small compared to other objects in the universe. Okay, let's zoom out from Taiwan to Earth. I think you know Earth. The size of Earth is about 6,000 kilometers, and mass is typically 10 to the 24 kilograms. And as you know, Taiwan is only a small part of this Earth, and we are only a tiny part of this kind of Earth. And let me zoom out more and more from Earth. When we watch sky, we can find sun. And the typical size of sun is about 0.7 million kilometers. This is about 100 times larger than Earth in terms of size. As you know, the volume is proportional to length to the power of 3. Do you know? Okay? Centimeter and centimeter cubic. So in terms of volume, this is about 10 to the 6 times larger than Earth. But in terms of radius, this is about 100 times bigger than our Earth. And the mass of sun is about 10 to the 30 kilograms. This mass is a kind of typical mass of stars in the universe. And from here, we will use this mass as unit of mass. Is it okay? When we compare something and kilogram, then we can measure how much kilogram this object is. And like this, we will use solar mass as a unit of mass from here. And when we zoom out more and more, we will find a solar system. Do you know solar system? Okay. Solar system is composed of many objects. And there is sun, for example, sun, and planet, and comet, and asteroid. The typical size of solar system is something like this. And mass is typically 1 solar mass. And all of these objects, including asteroid, comet, planets, are bounded by the gravity of sun. So they are, let's say, all of these objects are bounded by suns. This is the definition of solar system. And let me zoom out from sun. Then we find our nearby stars. This is not sun, but different star next to Earth. And typical distance to nearby star is about 3 parsec. And 1 parsec is 3 times 10 to 18 centimeters. And this is typical distance from one star to the other stars. Okay. So far we find only 2 stars, but when we zoom out from here, we can find our galaxies. The typical size of galaxy is, the radius of galaxy is about 10 kiloparsec. 10 kiloparsec is about this distance. And the total mass of galaxy is 10 to the 12 solar mass. Can you understand it? It is 1 solar mass times 10 to the 12 solar mass. Okay, let me ask one question for all of you. From this information, we can naively estimate how many stars are in galaxy. Typically, the mass of one star is about 1 solar mass. Okay, mass of star is 1 solar mass, and total mass of galaxy is about 10 to 12 solar mass. Then, how many stars in galaxies? Please raise your hand. A? No? B? B? Okay. C? Oh, thank you very much. In some universities, some people raise hand to A. So I'm very happy that all of you raise your hand at B. But the answer is A. Our galaxy contains about 10 to the 11 stars, and the rest is so-called dark matter, not star. So the mass of our galaxy is about 10 to the 12, but only 10% is stars, and almost all of them are so-called dark matter, and we cannot observe this dark matter directly. Yeah, thank you very much for raising your hand at B. Okay, this is a galaxy, and let's zoom out from galaxies. When we zoom out from galaxy, we will find some clusters of galaxies. Sorry, this is a bit difficult to see. Here is Milky Way galaxy, and there is some so-called dwarf galaxies. They are bounded by our Milky Way galaxies. And we can find also Andromeda galaxies. They are nearby a very big galaxy to us. And these structures form so-called local groups. This is a group of galaxies, and it contains about 50 galaxies in this group. And it's not end. We can zoom out more and more. When we zoom out from local group, we will find so-called galaxy clusters. This one galaxy cluster is typically composed of about 1,000 galaxies. So this figure is not good, but in some scale, we can find about 1,000 galaxies clustering in some scales. And when we zoom out more and more, we can find so-called superclusters. This is largest version of clusters, and our Milky Way galaxy is maybe around here, and this supercluster composed of about 10 to the 5 galaxies, 100,000 galaxies in this structure, and typical size is about 160 megaparsecs. Mega is 10 to the 6, and parsec, can I use this here?
There's some markers on the desk.
Okay, thank you very much. Okay. Parsec is about 3 times 10 to this value, and so 100 megaparsec means this value times this value times 100. So it's very big structure in the universe, and these superclusters compose of so-called large-scale structure in the universe. When we observe galaxies and make galaxy map, we can find this kind of structures in the universe. For example, when we see here, there is many galaxies rather compared to other places. For example, here or here or here, and there is very few galaxies in these regions. This kind of structure is called large-scale structures. And one interesting point is this kind of structure is created from very tiny fluctuation in the early universe. In early time, universe is much smaller than current size, and there is some kind of so-called quantum fluctuations in the very small initial universe. And as it expands, the initial quantum fluctuation grows, and this kind of structure is created. It's very beautiful theory, but a bit difficult to show here. Okay. Let's move to more large scale. When we go more large scale, we can find so-called observable universe. We can find observable universe. Okay, so far we start from humans. We just show large scale structures from human to observable universe. As I show here, there is very large parameter range in terms of size. For example, the order of this size is from 10 to minus 10 to 10 to 30. So the range is about 10 to 40. The range is about 10 to 40. And in terms of density, the parameter range is about 10 to spans in 10 to 50. So it's very important to find where is it's very important to find where the object is in this plot. Is it clear? For example, when we see sky and we get some observational data, and from that data we have to conclude, oh, this object should, for example, here or here or here. This is very interesting point of astrophysics, but sometimes a bit difficult. Today, I focus on neutron stars. I would like to very briefly introduce how we can estimate the position of object in this plot. For that purpose, very famous problem is so-called Fermi problem. This problem is named after Enrico Fermi. He is very, very famous physicist and got Nobel Prize. And by the way, I want to ask students, do you know this kind of problem? No? Okay, thank you very much. Okay, then let's start in initial part. Okay, this is a kind of, quiz. How many piano tuners in Chicago? We don't know detail of Chicago, but typically this problem means how many piano tuners in one city. Okay. At first, I think all of you cannot answer. You don't remember how many tuners in your city. Okay. So we have to calculate the number of piano tuners based on our daily lives. This is Okay, let's assume some parts. Let's put some assumptions based on our daily life. The population of one city is 3 million, and three person compose one families. Okay, and of course some of your family is about 1 people or 2 people or 5 people. But here, as I mentioned at first, we don't care detailed numbers. We just showing the order of magnitude. Okay, we just assume 3 person makes one families, and about 10% family have pianos, and one piano is tuned once per year. These assumptions are based on our daily life, and not so. These assumptions are based on our daily life, and it's not unnatural assumptions. And here is the assumptions for piano tuners. One tuner tunes 3 piano per day, and one tuner works 550 days per year. These two are assumptions, and I'm not sure, but don't change the orders of these values. Okay, then let's estimate number of piano tuners in one city. First, we can estimate number of pianos in one city. Number of piano is let's start with population. 3 million people are in one city, and 3 people makes one family. So this value represents the number of family in one city. And when we multiply 10%, we can estimate the number of pianos in one city. And next, we can estimate the, how many pianos one tuner tunes in 1 year. One tuner tunes 3 pianos per day, and one tuner works these days per year. So just multiplying this value and this value, we can estimate the number of tunes per tuner per year. This value, and number of pianos is this value. So just dividing this value by this value, we can estimate number of piano tuners in one city. And the answer is about 100 tuners in one city. This is, initially, I think it's difficult to answer these questions. But based on these natural assumptions, we can estimate how many tuners in one city. Okay? This is what we did in astrophysics. In astrophysics, these assumptions are made based on physics in these days. And using physics and some assumptions, we can estimate where is object in this map. Okay, let me start introduction of neutron stars. Neutron stars are discovered as pulsars. So at first, I'd like to introduce I'd like to introduce the discovery of pulsars. Pulsars were discovered by Bell and Hewish in 1967, and they observe sky in radio band. And here is the signal what they detect. And you can find some peaks in these curves here, 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 here. You can find these peaks. And when they analyze these peaks, they found that the period of this signal is 1.337 seconds. Okay, it's very interesting point because when in our daily life we cannot find this kind of very accurate clock in nature. Okay, we cannot find this kind of very accurate clock, but they found this kind of accurate clock in radio sky. And because this is very accurate, some people are discussing this may come from this signal is made by aliens. But nowadays we know that this signal comes from very compact stars. And this is very naive figures how this kind of signal is created. Assumption is very simple, and this is like a lighthouse in our daily life. One star is rotating, and the radio emission is beaming in some directions. And when we can see this beam, we can observe this kind of peaks. This model very naturally explains 1.337 seconds. Okay, this is just a kind of very simple and easy model, and we can believe this kind of models. Then, based on this fact, let's estimate what is pulsar. This is okay. Here we use physics to understand the pulsars. For this object to be star, the gravity should be stronger than centrifugal force. Do you know these force? Okay, okay, you know. If you don't know, please ask. This is like a rotating pizza. When pizza chef makes pizza, they rotate and it expands. Okay, this is in force balance between centrifugal force and tensions of pizza. So if pizza chef rotates pizza very fast, this pizza will break. It's natural, okay? Same condition should be satisfied for stars. The centrifugal force of this object should be smaller than gravity. Otherwise, the star will break like rotating pizza. Then, based on this assumption, we can estimate some values of this object. From Newton gravity, we know the gravity is proportional to, gravity equals these values. If you don't know this equation, let's understand large mass means strong gravity and small size means strong gravity. It's okay? Large mass means it's okay? Large mass means strong gravity, and for fixed mass, compact object possesses more strong gravity. It's very natural. And centrifugal force is shown here. Omega is angular velocity, this is a kind of okay, here. The angular velocity is 2 pi divided by period. So when period is small, angular velocity is large. It means it rotates very fast. And centrifugal force is proportional to R times omega squared. It means when size is large, centrifugal force is very strong. And when we rotate objects very fast, centrifugal force also increase. This is very natural and consistent with our daily life experience. Okay, just comparing these two values here. Okay, we don't do something difficult, just compare this value and this value. And just using this equation, we can estimate the density of these stars. And when we rewrite this equation from here to here, we find that the density should be larger than 10 to the 12 gram per cc. So based on very simple model and based on very simple physics, we can estimate the density of this object. Then let's go back to this diagrams. The density should be larger than 10 to the 12 gram per cc. So only possible solution is this star is made by quark or nucleons and not made by atoms. This is very simple. And by this calculation, we can conclude that the rotating object is neutron star. So just by using this simple calculation and using simple physical model, we can conclude that this rotating pizza is made by neutrons. And nowadays, we observe many signals from neutron stars, and we know that the size or mass of neutron stars. Okay. This is a typical size of neutron star. Typical size of neutron star is about 10 kilometers. It's very, very small. Okay. Here is Shinchu, and here, this is the size of neutron star. It's very small, but this neutron star have the same. The mass of this neutron star is the same as Sun's. Okay, so this is very, very dense object. The mass of Sun is concentrated on this size. It's unnatural from our daily lives. And this density is comparable to the density of nucleus. Okay. Then, question is how this kind of object is formed in nature. Okay. But before going into detail of neutron stars, I would like to introduce what is stars. What is star? I think you know Sun is different from Earth. Okay, And Sun is so-called star, and Earth is so-called planet. They are different. What is the difference of these objects? The difference is Sun is shining by itself, and Earth just reflects the light from Sun. Do you know? Okay. Okay. This is different of Sun and Earth. And okay, why sun can shine? This was a big problem in early astrophysics, but nowadays we know the energy budget for this sun is nuclear energies. So they burns hydrogens and shines. So in this point of view, a star is an astronomical gas sphere, and it generates energy through nuclear fusion at the center. Sun is very big, and due to that huge mass, the density at central region is very high, and and at this central region, nuclear fusion occurs. Hydrogen makes helium and deposits some amount of energies. And this energy is the source of light from sun. So it means their sun is shining, but they just consume some fuels. And this fuel is hydrogen nucleus. When sun burns many hydrogens, then they will lose fuel for they will lose fuels like this. And what happened at that point? This is so-called death of star. At the central region of star, hydrogen is burned and helium is formed. And next, helium is burned and carbon is formed. And this kind of nuclear fusion proceeds, and from hydrogen to ions. But iron is the end of this kind of nuclear fusion, and when iron is formed, nuclear fusion cannot occur above this point. So they lose fuels for nuclear fusions at this point. Then they lose energy budget, okay? The energy budget was nuclear reaction at central region of sun. And when nuclear reaction stops, they lose energy source for their shining. Then they just emit their energies from sun to environment, from star to environment. Sorry, not the sun. We consider stars with mass we consider more massive stars compared to suns. Then this star loses energies. Then it just cools, okay? When one star emits radiations, it just cools down. It loses energies. And due to this radiation, temperature decreases, okay? When they lose energy, the temperature decreases. And when temperature decreases, pressure also decreases. Do you know how to say? I forgot. Equation of state, okay? PV equal, I think you may learn PV equal nRT, nkBT, or such kind of equations. Based on that equations, when temperature decreases, pressure also decreases. And then gravity becomes stronger than pressures of gas. And star just collapses to center. And when initial mass is up in this value, the star so-called supernova occurs. They just due to strong gravity, they just collapse, and at some size it bounces. And at this point, neutron star is created. So neutron star is a kind of dead body of stars. Stars are shining by nuclear reactions, but when they lose nuclear fuels, they cannot shine. It's a death of star, and dead body of star is neutron stars. This is this is how neutron star is created. And one interesting point is when supernova, some, for example, carbon or oxygen or silicon is ejected from these stars, and these objects compose of our bodies. So I think all of you have bodies. All of you have, for example, carbon or oxygen in your body. Okay, and that kind of object is formed, is created in this kind of stars. That object are created inside stars. Okay. This is a very brief summary of evolution of stars. When star evolves, they experience supernovas, and in some cases they form neutron stars. This is the flowchart of the life of stars. In some cases, neutron star is created, but if the mass of star is much more massive, then black hole can be created. Black hole is also interesting, but today's topic is neutron star, so I will focus on this part today. Okay, this is how neutron star is created. Oh, I have some time. Okay. Then, let's consider pulsars in general physics class. Okay. So far, I introduced pulsars from astrophysical point of view, and from here we will use physics to understand pulsars. From observation of pulsars, we can observe the period of pulsars. Okay, this is initial part of I introduced this part at first, and in addition to period, we can estimate time derivative of period, time evolution of its period. Initially, neutron star is rotating with this angular velocity, but as time goes, the spin period decreases. Can you see the difference from here and here? Initially, it's rotating with some period, but as time goes, the period increasing. It means rotation velocity is decreasing. Okay. To understand this kind of change, let's consider a very simple model. Let's consider a spinning top in the universe. I heard that this class is not this class is not for those who are not focused on physics. So for some people this slide may be very you know all of these points. But let me explain. Let's consider not spinning top. Okay, they are at rest. At this case, they are not rotating, so there is no period for this object. And as you can understand, the velocity of this rotating object equals 0. Okay. Okay. It's just it is not moving, so there is no velocity in this object. So kinetic energy of this object is 0 because they are not moving. Then let's consider a spinning top of with radius of r and mass of mass of m. They rotate with period of p. Then the velocity of this object is about r divided by p. It may be a bit difficult, but how to say? R is the typical size of. Okay, let's consider the rotation of this stick. I rotate, for example, let's consider I rotate this stick with period of 1 second. Then the velocity at this edge is radius divided by, ni pi times radius divided by period, okay? This is radius and it rotates with distance of ni pi r in period of p. So typical velocity of this rotating object is r divided by p. And this is kind of velocity, and using these mass and velocity, we can estimate kinetic energy of rotating spinning top. This is just m times v squared. I think you may know. Some of you knows the expression of kinetic energy, which is equals 1 over 2 mv squared. But this is astrophysics class, and we don't care 1 over 2 or 1 over 3 or 3 pi or such kind of very important but tiny numbers. We don't care that kind of numbers here. And if you know mechanics, this is kinetic energy is expressed something like this. This is momentum of inertia, and omega is angular velocity, and I is about m times r squared, and this is about p to the power of -1. And this combination equals these combinations. If you know mechanics, that kind of expression may be useful to understand. Then next, let's consider the decay of spin. When we rotate spinning top, it spins very fast initially, but as time goes, the spin velocity decreases, and at some time the spin will stop. And as I mentioned in previous figure, at this time, it has kinetic energy. Kinetic energy at this phase is not zero, but here kinetic energy equals 0. So from here to here, it loses kinetic energy. Okay? It's, I think, natural. And we can calculate energy loss rate of spin kinetic energies just taking time derivative of kinetic energy. Do you know derivative, time derivative, or okay? Okay, maybe you know. In time, the shape of spinning top is fixed, fixed mass and fixed size. So m and r is independent of time. They don't care time derivative, and time derivative just affect here. It's period, and I expect you can calculate from here to here. When we calculate time derivative of this value, we can connect energy loss rate and time derivative. At here, additional factor 2 is ignored here. So spin down means spin down means increasing p. It means positive p dp dt. Means positive dp dt means period is increasing, and it is called, this process is called spin downs. And positive dp/dt means negative kinetic energy. And kinetic energy. Positive dp/dt means negative dE dt. So kinetic energy is decreasing as period increase. And we can connect this value to this value. Then, in case of spinning top on the Earth, why do spinning top lose spin kinetic energies? Do you know? Okay. They lose their kinetic energy by frictions. It's very important point from this model. Because of friction from at this part or in air and this spinning top, they lose energies. This is in case of spinning top on the Earth. But now we are considering spinning top in the universe. Okay? So there is no friction between this object and some other things. Okay? There is no frictions. But their period is increasing. So it means this object loses its spin kinetic energy by some process. But we don't know. But there is no friction. So some additional scenario is we need some additional scenario to dissipate this kinetic energy. Okay? And the answer of this is radiation, but it's a bit difficult to understand at this point. So let's consider very simplified model. Let's attach magnet to this spinning top. Okay. So far we are considering spinning top and just attach magnet to this object. When we attach magnet to object spinning top, then as it rotates, the direction of spinning top changes. Initially, spinning top is in these directions. But as time goes, the direction changes from here to here to here. Something like this, okay? And important point of this change is not only magnetic field, not only magnet, but also the magnetic field around this spinning top is also changing. Initially, magnetic field is something like this. Magnetic field is from something like this. Initial magnetic field is something like this. But when it rotates one pi, then that magnetic field changes from this shape to this shape. And then it returns initial conditions. So as time goes, the magnetic field, the configuration of magnetic field is changing at here. What happens next? This is an animation of spinning top. At the center, there is spinning top with magnet. And this, as you can see, as spinning top rotates, this is, I think this color represents electric field. And a wave of electric field is emitted from central region to outer regions. I think this is a topic of this class. Did you already learn this point? Maybe no. Maybe no. Okay. Maybe you will learn this point later. But when a magnet rotates, it emits electromagnetic waves. And electromagnetic wave carries energies. So when this kind of magnet is rotating, then energy is emitted from this object to outer regions. From the point of view of energy conservation, let's consider energy conservation laws. This emit energies. It means some energy loss should occur at this central point. Is it okay? When some object emit energies, then this energy should be, there should be some energy budget for emitted energy. And in this case, the spin of magnet is the energy budget for this emissions. Okay. And I think you may learn this kind of equation later in this class. But from undergrad level physics, we know that the energy loss rate of this electromagnetic wave is something like this. C here R is size, C is speed of light, and B is magnetic field strength, and P is period. And important factor is this B squared and P to the power of -4. It means when magnetic field is strong, emitted energy is large. Okay? Large B means large L, and it means more energy emissions from system. And small p also means large L. Small p means fast spins, and by this fast spinning, they lose more and more energies. Okay, so far we review some. So far we create some very simple model based on general physics. From observation, we can observe P period and its time derivative. And using this information, we can estimate the energy loss rate of its kinetic energy, dE dt. And when we assume spinning top with magnet, we can estimate energy loss rate. This is proportional to B squared P to -4. And when we just assume this value equals this value, we can connect observational value and magnetic field. Is it okay? It's okay? We just use very, very simplified models and just use physics of undergrad level. And just by using this very simple model, we can estimate the magnetic field of pulsars. And this figure shows observed period and period P dot. This axis shows period, and this axis is period derivative. And by this estimate, we can calculate magnetic field of this object. And here is magnetic field of this object. And typically, the magnetic field strength is about 10 to the 12 Gauss. And this value is much, much larger than what we can create on the Earth. This is this is a maximum magnetic field on the Earth. It's about 10 to the 7 Gauss. And after making this magnetic field, this laboratory breaks. So it's very difficult to make this magnetic field on the Earth. But pulsars possess about 10 to the 5 order of magnitude strong magnetic field compared to this value. And sorry, this figure is not accurate, but situation is something like this. We are here and we find many pulsars. It means we find many magnets, strong magnets in our galaxy. And so far we detect about 3,000 or 4,000 pulsars, but from theoretical point of view, we expect the total number of pulsars is about 30,000. So we just find about 10% of all of pulsars. And okay, this is a bit maniac part, but let me explain. For many pulsars, the spin down luminosity is larger than photospheric luminosity. We can observe period we can observe period and p dot dp dt, the time derivative of period. And from that information, we can estimate spin down luminosities. And when, in addition to this, we can observe pulsars by by telescopes. Sorry, not telescope. In other band, this pulse comes from radio band, but we can observe this object by optical telescope or X-ray telescope or gamma ray telescope. And for many pulsars, this photospheric luminosity is smaller than spin down luminosities. It means the spin down energy can support photospheric luminosities. Okay, this is very natural. Pulsars are spinning and it loses its spin kinetic energies. And this spin kinetic energy can support what we can see. And these guys are called pulsars. But for some pulsars, photospheric luminosity is larger than spin down luminosity. As I mentioned, spin down luminosity is energy budget for pulsars lose spin down energy, and this spin down energy can be converted to photons, and we can observe photons. But for some pulsars, the luminosity of a photon is much larger than spin down luminosity. It's a kind of different from what we expect. And in this diagram, these guys are shown here. And from calculations, we know that these guys are typically have relatively strong magnetic field. And this photospheric luminosity from these pulsars are thought to be energized by magnetic field. They lose their kinetic energy, but in addition to this, they dissipate its magnetic energy, and this magnetic energy can be converted to photons, and we can observe these kind of emissions from these pulsars. And these pulsars are called magnetars, very strong magnet in the universe, and they show many interesting bursting activities in X-ray, gamma ray, or radio band, but I will skip this point. Okay, this is a summary of this talk. Summary of pulsars. Pulsars are very extreme environments. They possess strong gravity, high density, and strong magnetic field. And they show some of them shows diverse bursting activities. Okay, here is summary of this talk. Summary of this talk. Pulsars are neutron stars. We can calculate this point by based on very basic physics. Okay. And our galaxy is filled with these strong magnets, but we just observe some part of that that magnet, and future observation is expected to explore more details of this kind of pulsars. Okay, thank you very much.
Thank you, Dr. Tomoki Wada, for the interesting talk. Any questions from students?
Too difficult or too easy?
No questions?
I have some question about dimension, because usually in engineering we use meter as a basic dimension, but in astronomic I see usually using
centimeter.
Yeah.
Why?
Are there any reason?
We usually use so-called CGS Gauss unit, centimeter and grams and second. And I think it's nothing special, but in terms of electromagnetism, we use CGS Gauss unit, because in CGS Gauss unit, electric field and magnetic field possess same dimension. Okay? In MKSA unit, there some appears, I forget the name, something like this one or this one. And we should connect dimension of magnetic field and electric field using these values. But from the point of view of physics, E and B should have same dimensions. How to say? Yeah, for example, in CGS Gauss unit, the energy of electromagnetic field is proportional to just these combinations. So we don't need, how to say, additional these factors to tune dimensions. I think this is one reason why we use CGS Gauss unit in physics. And in astronomy and in elementary particle physics, they also use this kind of unit.
Thank you.
Thank you very much.
Any more questions?
In today's lecture, we learned about neutron stars.
Yes.
And when stars, like massive stars die, they become neutron stars.
Yes.
But I also heard that they can also become black holes.
Yes.
And how does that happen?
How
When
it's
some stars become neutron stars and when some become black holes.
It's very good question and difficult to answer. In neutron star, there is maximum mass. And this is a kind, neutron star is supported by nuclear force. And in order to sustain the shape, the nuclear force should be in balance with gravity. Okay? If gravity becomes much stronger than nuclear force, the nuclear force cannot support neutron stars. In that case, black hole is formed. And when it's formed, and this is the difference between this branch and this branch, and must determine these two branches. And when black hole is formed, for example, there is some, how to say, theory that black hole can emit like jet-like emissions. And this is one interesting point of the formation of black holes. Do I answer your? Sorry, my answer is okay? Or Are there any additional question or?
So if the gravity is stronger than the nuclear force, it becomes a black hole.
Sorry.
If the gravity is stronger than the nuclear force, it becomes a black hole.
Yeah. That is the how to say. That is the criteria between this branch and this branch. And maximum mass of neutron star is less than 3 solar mass. And when the how to say, object is much larger than or larger than 3 solar mass, then it should become a black hole. Okay, is it okay? Okay, thank you very much.
Any other questions? So if there's no more questions, let's thank our speaker again. So I think that is for the special lecture today. Thank you everyone for joining and see you on Tuesday next week.
Thank you. Is it too difficult? Or too easy?
At some part when you show the equation.
Equations.
Yes. Because most of students who is not from Department of Physics, they're from other departments. And they take this class.
Yeah, I try to as easy as possible. But